I doubt it.
Why is it up here?
It doesn't work, dude. Drive on.
Cool. Good.
All right, we're ready for the next talk, which is Hop Hacking Hedy.
How's everyone doing?
Awesome!
Good to hear. So, Hop Hacking Hedy, as our friend explained there, the three authors, one of which just ran away. Hopefully he'll be back in a second. But other than that, so Atlas, who is now departed somewhere, Cutaway, and Q, myself. Atlas is the code monkey and the magical debugging wizard. Cutaway here has been doing a lot of radio work for the project, and he is the supreme dongle overlord.
He has a supreme dongle. If you want to touch my dongle later, come on up here.
So
I'll show it to you.
you'll see dongle referenced in these slides quite a bit. Maybe we should preface that by saying radio dongles, USB dongles are actually, so it's not, a bit of a euphemism.
No.
All right, fine.
No.
And then, obviously, myself, creator of Sexy Slides and Hardware Foo. So, quick agenda of what we'll be going through today. We're going to start with a prelude, Hedy and our patent. Who actually knows what we mean by Hedy, or who we mean by Hedy, except for you?
I do.
I do.
Anyone else besides the middle? Do we have presents to give out somewhere? There's a Saint.
There's a Red Bull.
Oh, that was mine, but here, you can have it. You were the winner of a sugar-free Red Bull, because I've had way too many, so it's okay.
Jay, I've seen you on Red Bull. You're not getting it.
Yeah, no.
I've seen you throw, please don't.
What is the opposite of Red Bull?
Blue balls.
Same effect.
All right, so after the prelude, we'll be going through a couple sections about what we're actually here to discuss, frequency hop spread spectrum, FHSS. In the WTF section, we'll be explaining the technical details of the technology, usage and analysis, maybe some case examples, applications and implementations of the of the hopping patterns, and then we're going to show off a bit of our project and what we've been doing with this code. Cutaway's been doing a lot with the hardware section. Matt's got really good code to show, and we set up a Google Code project. So hopefully you guys can dig in and start there. So we already went through what is a Hedy. So surprisingly, not a lot of people actually understood the title. One guy kind of shouted it out, so we have a couple slides on her, because she is absolutely amazing. So yeah, the alternative title, which we didn't think ShmooCon would really appreciate, is up there. 3 dudes in a dongle. I guess that's the joke, right? So this is Hedy Lamarr, once kind of dubbed the most beautiful woman in the world, Austrian American. Come on, that's it? Hedy Lamarr, people. Yes, come on. All right, so Hedy Lamarr, Austrian American actress, but a lot of people, back then at least, a lot of people know now, especially in this room, that she was an inventor. She was a scientist. She actually was really, really brilliant, and she did really cool stuff. So yeah, we're kind of interested in the former part there, the inventor, not so much the actress part, obviously, unless you're
Unless you're into dead chicks.
Yeah, there's
Yeah,
that.
go Josh.
Necrophilia, anyone?
Let's hear it for Tom Petty.
Does anyone have shmoo balls? Because that definitely warranted one. So just a side note and a bit of a gripe.
That is a
I spent
target.
actually a lot of time, I was kind of focused around Hedy Lamarr for a while, and they kind of pulled me off it because it really doesn't have a lot to do with our talk besides the original patent. But yeah, just a bit of a gripe. She was used kind of more for her actress talents when she was alive anyway than she was her scientific prowess. And I think that's, it was financially smart for the military.
Way
to do
too
that.
Hedy-centric. Move along.
Yes. But yeah, so her and
This
George
boy
Abdal-
has no girlfriend right now, I don't think. So
This is on Ustream, man.
3 guys in a dongle.
Yeah, there's That's probably the reason, right? I named. So,
Go Q!
so along with George Antheil, she came up with a really interesting patent and called Secret Communication System, which we're going to review real quick. Just a quick nod to EFF. The reason she is kind of so well known, in '97, EFF actually gave her an award for the work she did with the frequency hopping, the code. So just a quick look at the patent, because I think it's really interesting. The drawing is actually pretty difficult to see, and so I'm going to do a little bit of explaining here. I wish I had a laser, but if you see the the top side here.
Where?
I can't point. Oh,
Yeah, you
is this
can.
actually a laser?
Yeah.
How do you use it? There we go.
Press the laser button.
This is not strong enough. Anyway, top half. Yeah, top half. What we we have the left side. You see the piano keys. So what happened was, her and George Antheil, who was actually like a composer, a musician, they actually created this technology originally using two sets of pianos and 88 keys. And the rolls you kind of see on the right there that kind of look like two wound circles with the paper going through it. That's
This one?
actually, yes, thank you. That's actually a paper roll. And if you know anything about the older pianos, it kind of kept a sequence of keys that the actual piano would play automatically. And so that was actually fed into the piano to create the hopping pattern of 88 keys to decide what frequency channel the transmitter there was actually going to transmit on. And they were both synced using the same piano rolls. So it's, bit of a, just kind of a really cool thing that I dug up that I figured some people might enjoy. So anyway, let's get into what we're here to discuss, frequency hopping spread spectrum. So this is it's basically a transmission method. And what happens is the carrier randomly switches between a finite amount of frequencies.
Not random.
Yes, pseudo-random. Definitely not random. Frequencies within a domain. And usually there's, as we see with a couple examples here, usually there's a certain amount of bandwidth that you use. I think there's a minimum of like 26 megahertz that either IEEE or one of the standards actually recommend for legally doing frequency hopping. And depending on that, Bluetooth, as some of you guys might know, 79 megahertz bandwidth with 1 megahertz channel spacing, which means, every 1 megahertz there's, the possibility for a frequency or a carrier wave. We get 79 channels. So those hopping patterns, the total amount of hops that they're actually, reduced to is now 79 channels within some type of pseudo-random sequence. The second example here, we show, some of the smart meters that, have a 26 megahertz bandwidth, a little smaller of a channel spacing as well, and they do up to, some of them do up to 52 channels. So yeah, as we mentioned, kind of a pseudo-random sequence to choose the frequencies, and this is definitely known by the transmitter and the receiver. Obviously, they have to have some type of syncing method, right? There's four different syncing methods that they use. One of them uses kind of all the channels. One of them kind of plays catch up until the timing is actually correct, and then they sync and follow along. But, no matter the actual sync method, this is stored in an algorithm somewhere within memory of the device, or, if you're Hedy Lamarr, it's stored on a piano roll, which, is pretty badass, right?
Yeah!
So, just some usage characteristics, or some usage implementations that we've seen. The first kind of major proponent of this is the military, obviously, with all really cool technology. They're always kind of, I'm not going to say up to date, but they're there with some really good. They're there with some really good technology, and it's kind of up to us, in the security community to be like, okay, let's analyze what they're doing, and maybe we can voice our opinion to kind of help out. So one of the implementations here is called SyncCars, and it's a single channel ground and airborne radio system. really long acronyms. Obviously, that's how you know it's government related. And this actually can do voice and data. It has 25 kilohertz channel spacings, between 30 and 88 megahertz bandwidth. And so, technically, if my math is correct, you get somewhere, depending on what actual bandwidth you get, somewhere between 120 and 350 some channels. The problem is 100 hops per second is pretty slow, especially when it's compared to Bluetooth. Bluetooth's what, like 1,600 hops per second. So, it is expected to be replaced by an SDR solution, but they've had deployment issues for a while. I don't know if it's actually been replaced or not. So the problem in this situation, again, is they've sold their 500,000th unit of this actual device, right? So you have, even if you're upgrading, even if you're getting that, that new solution, the software-defined radio, they're jumping into the, the new age, you still have 500,000 units that are all working on this old kind of technology, right? And they're not just going to jump those, right? You're gonna kind of try to make that a bit backwards compatible, and when that happens, you're kind of introducing a lot of vulnerabilities into this situation. So how many, so the upgraded JTRS radios that the military is now using do actually do SIP and do some voice encryption and data encryption through the the transmission lines. But again, if you're relying on 500,000 units of the old stuff, you're still going to see a lot of outdated hardware. So obviously, a lot of people know, the big B, Bluetooth. This actually uses kind of an advanced function of frequency hopping. They actually added a bit to it, and they do adaptive frequency hopping spread spectrum, which is, I guess the only difference is really if it sees a lot of noise or sees a lot of data on the channel, it automatically starts hopping, which has its own issues. But bandwidth of, as we went over this, 79 megahertz, 3,200 clock cycles, hops every other clock cycle. So, this one's about 1,600 hops per second, a lot faster than the military's 100 hop per second amateur radio usage. So what's the problem in this situation? What's the vulnerability or the attack vector? Is basically, as we saw, if you guys were here last year, Osman did an all-channel Bluetooth monitor device setup using USRPs and basically generating entire hopping patterns within 24 hours and searching the hopping patterns for the solution. So we can't really rely on frequency hopping as a primary implementation or security model. We obviously have to do a bit better than that, and obviously include encryption in what we're doing. So when doing a bit of research, like the first PDF that kept coming up, I read through it a couple times, and I actually didn't notice this line until like late last night, so I decided to throw it in here. But it's basically a paper describing implementations and practices for frequency hopping, and one of the things that I read over like 3 or 4 times, I'm like, oh, okay, that doesn't make a lot of sense, but I'll keep going. I kept going back to it. I'm like, all right. So it acts as a layer 1 encryption process. Really? How does it do that? And again, right, their mindset is, all right, it's way too fast.
No, the patterns, it acts like a password.
Yeah.
Really?
Yeah, so their feeling is, it's, you can't catch us. We're the road runner of frequency hopping technologies, right? And apparently that doesn't warrant any application level encryption at all. So, we see a lot of this referenced in a lot of different papers, and you have to take this thing seriously because a lot of engineers and a lot of developers and implementers and such, they aren't aware still of security, no matter how much we keep talking about it and how much we kind of, it's all obvious to everyone in this room, but what is that compared to the percentage of developers in different industries and which exist? So, the best thing that we could do again is present research, present projects, keep on this, and hopefully, By being proactive and by being, reasonable and working with people, we can actually start to change things. So, frequency hopping analysis, why do we keep using it? It's very efficient, and what I mean is it keeps a lot of noise out of the bandwidth, right? So there's an overuse problem, or people kind of suggest that there's overuse problems in unlicensed bands, anything from 900 megahertz or any of the ISM bands, right? And it's really good to use frequency hopping in those bands, and it is a good idea, right? So only because it kind of keeps things on different carriers and not on the same, not on the same frequency range as if you were some type of licensed protocol. So in that aspect, it is ideal for efficiency, but not security. Some of the attack vectors. So obviously, you must have the hopping pattern to jam or receive the entire data stream. This was the entire intention on actually when it was created. Hedy Lamarr actually developed this for military reasons to prevent the jamming of our radio-controlled torpedoes. So, to actually jam. Anti-jamming is one of the overall benefits of the technology. Again, there's the always very well-known pseudo-random number generator break. If you kind of realize that the low amount of entropy or the not so randomness of the generator that produces the sequences in which you're hopping, that becomes another attack vector. Analyze channel data in time fast enough to catch the hops until repeats start to occur. And this is kind of the idea on what we get started thinking about when we decided to start the project. And then there's generate the entire pattern for all clock values, which is the last attack vector, which we saw in the Bluetooth paper. So kind of the solutions, which I went over a bit, but we've seen this in other industries, right? People have solved this problem. The point for us, creating this project is not only is it fun, not only do we get to play with really cool hardware, it's the idea of okay, let's solve a problem and prove that listen, with really cheap hardware and really novice skills, you can actually produce a tool that'll actually be able to decode these hopping patterns, be able to actually be a legitimate vector against a lot of these implementations that everyone is using, military, commercial alike. And just as an example here in the smart grid industry, we have seen some of the first generation devices use frequency hopping as a primary prevention of eavesdropping. Obviously, if you're switching channels, data stream on each channel, you kind of have to again follow that hopping pattern to decode what that meter is saying, right? But in the second and third generation models, they've actually, or we've actually, recommended, different types of encryption and secondary kind of, methods of securing the transmission and not relying primarily on frequency hopping. So yeah, do not rely on a single point of failure. So to talk a bit about the project, just the inspiration, again, false assumptions that speed in pseudo-random sequence creates a secure transmission. Very, very untrue, especially with the amount of technology we have now. So, our thought is let's build some devices. Let's build some devices that could be configured for known ISM bands, real easy to do. They could do, another feature would be, which we finished or are working on, is automatically analyze channel spacing and decoding of the actual patterns or spread codes. So create this code base with far-reaching capabilities for people to use. And to sum it up before we get started on the hardware and the software of what we're actually doing, so in 1942 they created this technology. Basically after 69 years, it's time to upgrade. So Cutaway is going to go through the hardware section and talk a bit about what devices we've been using and what the hardware looks like on our project. So. Yeah.
job, Q. Thanks a lot. Everybody, I'm Cutaway. I've came over to the Indie Guardians team about 6 months ago and dropped off the face of the planet. And the reason for that is I always considered myself a jack of all trades. I thought I had a lot of knowledge about a lot of sections of the industry, and I actually did. And then Atlas got me involved in hardware, and I learned that I didn't know anything about it. So the last 6 months of my life has been boot camp on hardware.
Becoming a master, baby.
It's Supreme Dongle Commander.
Commando. So what this actually started out for me is we knew we wanted to start taking a look at FHSS, but I really needed to get involved from the hardware level, understanding how the hardware interacts with firmware. So that's how I started on the project. And this is my walkthrough of that progression. So one of the things as a Marine, one of the things I have a problem with is failure. I don't like to fail. And well, you know what? It's just gonna frickin' happen in hardware. All right? This is probably making Travis cringe right now. We've got my hardware graveyard that's growing all the time, my good fat graveyard. We use these very extensively.
Wait, dude, that's mine.
Yes, but actually the first thing that I really boogered up was Atlas's dongle for his Cronus watch.
Quote board.
As you can see, on the only way to flash firmware on this thing is the debugging ports on the back end of it, and you see the picture of it. And I tried to, I learned the hard way that you shouldn't use lead-free solder, and because it's bad. And so now I do. I use leaded solder. But basically this broke off. So the one header broke off, and if you look really closely, you can see that the pads are lifting off of this. So basically, I completely hosed.
It's only ground.
The way that he can flash his watch. So hey, yay! So the point behind this is, and the point I'm trying to make is that when you're getting into hardware, you're going to break stuff. It's going to be expensive, but you get better with time. So what are my alternatives after that? I don't really want to, keep letting Atlas buy things and me breaking his stuff. So I started looking around at the things that I can leverage, and Travis and a bunch of people have been working on the Good Me project. Mike Osmond wrote some great firmware for that, and but I want to do my own stuff. I don't want to be on a project that people are really rocking and rolling on. So that was the con. Also, when I started thinking about what we're going to do with these things and presenting it to people, and every time that we pulled out and showed the spectrum analysis and showed them the little pink girl pager thing, like the glaze went over in their eyes and they started rolling their heads, and the conversation really ended really quick. So I wanted, if we're going to have something that we could show other people, I wanted to make sure that we had something that that they would pay attention to. So that's when I turned to the CC1111 EMK evaluation kit. And basically what it does is it's a CC1111. It's giving me the same thing, same capabilities that's in the IME, and we can program it with the GoodFet. We can communicate it with the data debugging. Travis and the other people who have worked on that, have really made a strong platform for that. So it's a great development environment. Plus, all the pins are already broken out. I'm not going to hose this one up as easily. So that's why that's why I started looking at this, and it really helped out a lot. So from there, obviously we're going to the firmware. I need to start working on the firmware. Hello World in the firmware talk is just actually making the LED blink. Well, yeah, it sounds easy, but the reason why we went to Cutaway Smash is because I started throwing shit at Atlas. Excuse me. I started, I've thrown a lot of stuff in my progression through getting some of this stuff to work. To do firmware, TI provides you with the IR demo environment, and if you want the full one, you can go and pay $8,000 for it. So that's one of the things that we're trying to get away from, is that we want to make sure that this is a low-cost solution. We're showing that people out there who don't have $8,000 for the development environment, that don't have $2,000 for a USRP, can spend $50 on a dongle, plug it into the computer.
We're working on a $20 option.
So that was kind of the point. But of course, we got to get the libraries from somewhere. So you can, when you're working on stuff like that, you can get the libraries from the TI stuff, but why do that when Mike's done a great job in pulling it all together in a compact package? So I just basically scraped everything from the IME project and really started leveraging that, and as you'll see, I started scaling it down. What I failed to do is listen to all the people that were providing advice to me, to Travis and Atlas and Q, and every time I tried to get these things to work, and every time I was throwing things at people, they kept telling me to go look at Smart RF Studio and use the information out of there. And when I finally decided to do that, things started falling together. So it was awesome. So this is definitely a key piece of software that you're going to need if you're going to be developing in the ChipCon chipset. You're going to need the information from there to help you get over certain humps, and then you'll be able to use that to start analyzing the code that other people have written and really understand what's going into a radio, because it's not just transmit and receive. There's a lot of other things that are going on there. I guess I can look right here, right? So now I know how to flash it. Now I know how to get firmware up on there. I've done the little hello world. So now I need to step back and start thinking about the rest of our project, where we want to be. And that is start analyzing, start thinking about frequency hopping. Well, what do we have? We've got a frequency range, and we know we need to do fast scanning. One of the points that everybody's making is that frequency hopping is too fast. Well, what are you using? Well, I'm using the CC1111 to do that. Well, what if I just use it? I can go as fast as you can. So, no, you can't. Oh, yes, I can. So that's one of the points that we're trying to make. I can scale down my the firmware. I can scale down the code to make the analysis go really fast and just detect things. I don't want to grab, at first I don't want to grab data. So that's one of the things that we started thinking of. So leveraging the IME code, leveraging the SpecCan firmware, I just started scraping stuff out. I just started whittling it down to make sure that it wasn't looking at the full range of frequencies. Also stripping out, obviously I don't have a display, so I had to strip out some of that, but I had to be concerned with the display capabilities provided by the IME is also helping with the radio. It's providing a delay and letting the radio sync, so I had to take that into consideration as well. And then pulling back to the good FET and leveraging the code that's provided by there, leveraging the interaction, and actually augmenting that a little bit so that it's providing a little bit more functionality associated with what we wanted to do. So what happened at the end, 2 days ago, is that I got 3 basic programs that we have. So we started off with the spectrum analyzer, and you can see the output that we have right here. The green line is the max values that we're receiving, and the red line is what they were receiving at that second or millisecond. Basically, what this is data that is being scraped off of by the good FET and just pumped out using a Python's GNU plot. And it's not as quick as the display provided by the IME, but as you can see, and we can see certain patterns developing, and that's what the second one was, the hop trans. We don't want to start on a device. If I just pull up a device that's doing frequency hopping, we're just going to be all over the place, and I'm not going to get anywhere. So what we did is basically I just created a simple program where we knew the channel spacing, we knew the channel numbers that they were hopping on, and we knew the hopping timing. And that's how we started our logical progression of whittling this down so that eventually, so we have something that we can start identifying hopping patterns.
It's the dead coon that you use to train your dog?
What this culminated in is what we're calling MinScan. This is taking the idea that when you're monitoring a device that is doing frequency hopping, there's always going to be a minimum level of noise. And so we take that information. We do we reverse from the max scan and start looking at the minimum that we're seeing within the environment. Pull that in, store that, and then add a minimum value of RSSI. We're monitoring the RSSI value and seeing when a frequency jumps above that range. And then what we do is we pull that data obviously off with the good FET, and you can see it right here. We just created a CVS file with the logical progression of hops that occurred. And once we got to this point, pretty much it's proof of concept that we can look at frequency hopping this way. And it's just a matter of determining channel spacing, speeding it up, and trying to figure out where they're hopping. And then from this, obviously, because of the size of the memory, and we'll talk about this in a second, on the good FET, we've got to do offline analysis for now, and then Atlas is going to talk about actually doing some analysis inline. So the issues that we have on this environment is basically, it's a development environment. So data debugging through the good FET is slow. What it does is it stops the CPU, pulls the data off, and then restarts it. So I'm missing that big swath of time, and it's probably, we can get that down to a second, but that's huge when we're talking about frequency hopping. So that's a drawback. Also, obviously, the memory, I have to scrape memory at a certain point, or else it's just going to overflow, or I'm going to overwrite my old data. So if I want more memory on the board, we're going to have to build a new board associated with that. Getting data off, we could do it via UART. I was working on that, but we actually got to the point, that's when Atlas came free, and he started developing a USB library. The chip, the CC1111 has USB capabilities, but it doesn't have it by default. It's not built into it. You have to implement it within the library. So you have to tell it how to communicate with USB. Well, the code provided by TI in the IAR development is it's designed for large projects, and it's bulky, and it's convoluted, and it's not going to be as fast as we want for what we're doing. So we needed to develop our own USB into the firmware to augment the MinScan capabilities, and that's something that Atlas will be talking about in a second. So my lessons learned, and these are for me personally. Basically, hardware is hard. You're going to fail. I had to learn how to fail a lot, and just get used to it. I don't accept failure. I just realize that it's going to be a part of the process, and I've really, I hope I've grown. Hardware documentation, I mean, they hammered it. Whenever I asked for help, when I talked to Travis, when I talked to Q, when I talked to Atlas, like, did you read the docs? Yes, I read the docs.
How many times was it actually a wiring issue? Was it like, oh, do you have it wired right? Yeah, of course.
Yeah, I'm avoiding that.
And for that one wiring issue, how many times do you say, yeah, done that? Yeah, done that. Yeah, no, really, do that. No, done that.
And then I read the documentation, and I realized that the pins I flipped the pins, so pin 1 was actually pin 10. So, yeah, so number 1, read the frickin' documentation. Pay attention to the documentation. And while you're learning it, shut up. While you're learning it, it's going to be hard to understand that. And that's just going to come with time. And also, I don't necessarily know if I can equate it to a NIST document, but there's just a
Please don't.
A ton. There's a ton of information in these documents associated with the capabilities. It's information that you need to know, but yeah, it's hard to sift through at first, so you'll get better at it. Radios are complex. Like I said, it's not just receive and transmit. There's a lot to do with clocking. There's a lot to do with frequencies, and there's the way that the chip actually handling it is going to be different across architectures. And so, find things that help.
Like the people on the stage, that bald dude right there, and Mike Osman's right up here in the front.
Exactly.
Make friends with people who have done it.
So, yeah, and steal their stuff. Mike, I stole Mike's stuff. So, using
Except
that,
Q.
so leveraging Mike's stuff, leveraging the information I got from these guys, leveraging the SmartRF Studio, I really started to understand radios. I'm still a novice at it, but at least I know where to go and where to be concerned about. So that's definitely something, if you're going to be getting into it, those are things that that's going to help you along. As far as the project go, what did I learn about the project? Is it something that is feasible? Absolutely. It might not completely play out in the end, but we're starting to whittle it down little by little, and that's the start of any good project. And actually, as you'll see in a second, they've taken my portion of the project, and we've really advanced it in the past couple days. And that's it. I'm going to turn it over to Atlas now.
Is this on the hard drive, or do I need that dongle in? Can I remove your
No, it's on the
dongle?
dongle.
Don't touch the dongle.
All right. That won't fit. Oh well.
Stand by. Talk. Just talk.
I like to move. All right.
Talk.
All right, you take care of it. Good. Hey, everybody. I just like to walk around because it keeps my brain moving. Otherwise, it like stops. So, yes, I am frequency hopping. So this all begins with, actually, I don't even know if these guys understand the true inspiration for my wanting to do this. I had a conversation with a smart meter vendor security guy from a company who didn't used to get security and now is one of the leading security companies for smart meters. And he actually sat me down and said, you know what? I know what you've been talking about. I want you to do it. And I want you to think of it this way. And so I'll try to use his terms as best I can. If I create a toy that you deploy in the field and leave it for 24 hours, and you break the frequency hopping pattern of one cell of a smart meter, or of a military grade installation, or insert favorite FHSS here, those deployments are so long-lived. What's a day? So the goal for me was to create a toy that could allow us insight and the ability to play, could be automated to leave it alone for a day or two, or heck, I don't even care if it's a week, and spit out a pattern that then I either just leave it in the tool and say, okay, turn into a network adapter, or I take it out and I put it into a different firmware as a NIC. I'm now on the network. So in my section, I'm going to have to go fast. Basically, I've had an hour's sleep. I've had 5-hour energy drink, 2 Red Bulls, and a Club Mate, and 2 cups of coffee, and I'm exhausted and like floored. Plus, I don't have any time. So we're going to talk a little bit about the CC1111 USB library that Cutaway mentioned. We're going to talk a little bit about the history of our tool. We'll show you a little bit about it, how it works, some of the stages of analysis that we're going to go through, and some of where we're going. Kick it. All right, so as Cutaway alluded to, the libraries provided by TI are convoluted and bloated. More importantly for hackers, difficult to read. You have to trudge through 20 to 30 different C or header files to figure out what's going on. So the main goal originally was, let's get this into 2 files, a C file and a .h file, and see what we can do. And that way we've got one place to go if we want to create a quick tool. Because when you're creating tools, the idea is quick turnaround, right? Because I'm ADD, what? So the CC1111 is a USB-enabled version of the most popular sub-gigahertz radio that's distributed throughout the world. Their idea of making USB easy is actually very frightful. As was previously mentioned, there's a lot going on there. And you might think, I love technical documents. I actually enjoy reading the CC1111 technical doc. Problem is, it's really cool for how to interact with the thing. It doesn't tell you a thing about, it doesn't tell you more than half of what you need to know about USB. So I turn to USB in a nutshell. Google it. If you're at all interested in doing work on this, or actually most of it's done here, but if you're at all interested in USB, this is an awesome document, gets you really going in the direction you need to as a developer. The other goal for this library was I don't need IAR because TI's libraries all require IAR. It's GPL, so I'm not tied to TI's anything. It's hacker written, which at this moment probably means very bad things, but in the end goal, it should be interesting to read and full of data, not a lot of fluff and multi-layers. Don? Okay, this isn't showing up very well. So,
Nice.
so basically, we met in the middle. I wrote the CC1111 USB library. Cutaway was writing the frequency, the radio stuff, and we eventually merged the code. And you can't really see it very well here, but this is the SVN log of our merging the code, and it starts with merge nearly complete, twice. Oops, twice. At least it compiles, still only MinScan and USB not even integrated yet. Doesn't freak out. Ping works, but I pulled out all the FHSS stuff. So the merge was like sick failure.
Right?
Oh, also, during the merge process, I managed to refactor Cutaway's code, which caused all sorts of nightmares for me, and he's trying to be patient with me when I screwed up his code.
Thanks for that.
Yeah, love you, Chief.
Scope creep is his new name. So.
My scope never creeped. So a little. This is my first venture into GNU plot. I'm kind of the guy who really loves green on black. So to see plots out of my stuff, that's actually pretty profound.
It's out of control.
So here's a couple screenshots. This is a plot of us doing some min and max scanning so that we can develop a floor and a ceiling so that we can start to identify, gee, what is a channel actually hitting? And a couple of plots of channel hopping over time. So this was this morning, which is why I had 1 hour sleep. I thought ShmooCon was in mid-February. Go ahead. Some things don't. Yeah, no hotel. So just a little intro to the code. My goal is to have you go out of here going, this is freaking awesome. I want to do some of this. So we've developed the C code for the firmware for the USB dongle. We have developed Python interactive code. Yes, you must be root. Sorry, it's libusb. But here's an intro. For the client side, you've got several dump something or others, which basically dumps large chunks of data to your client code. Get something or other is getting incidentals, like, hey, get the threshold right now. So the threshold being how high do I have to spike before I call it a channel. Deset. Okay, well, I don't like that value. I'm going to set it here. And during debugging and the state that we're in right now, that happens actually quite a bit. Then we get into the do's, like do floor and ceiling. So no, I don't mean like get out your spick and span. Do floor and ceiling does the min and max. So it scans through the channels hundreds of times, takes an RSSI value, and says, hey, is it above my max? Okay, readjust max. Is it below my min? Sure, readjust. Do channel ident. This is currently broken, but the idea is to take all the maxes and identify based on pattern where all of the channels are, or at least a relative spacing for channels. Because typically in a frequency hopping system, you will not have channels that are 3 kilohertz apart and then 20 kilohertz apart or whatever. It's clean, easy chunks. Now they may not use all the channels, but that's not quite that important. And then of course do hop tracking, which works kind of. I'm still working out some bugs there, but I'm really happy to say that we are plotting, we are identifying. I need to talk to Osman about a couple things. He and I departed like at what? It was pretty late. And then de-interpret. In case you hadn't guessed, when you start up the client, it creates a little variable called d. I like to work in interactive Python, so my shell prompt is greater than, greater than, greater than. So de-interpret actually comes from Cutaway bitching at me about, I don't know what to do with this code. Yeah, I hand him the client code, and he's like, I don't know what to do with this. What do you want? Huh? And so created deinterpret so that it would poll. See, I created this cool communications channel between the USB client and the USB controller. And so the client sends in data, the controller responds to it, sends back information from the dongle, and the client stores it in a mailbox, waiting to be picked up by whatever client you've got. It's really, really cool. Well, that wasn't good enough. So deinterpret repeatedly polls the mailbox, interprets the data because it's raw, spits out the right kind of representation, and then, if we so desire, it creates a plot of whatever type of information was delivered. Go ahead, Cut. So, frequency hopping analysis. The way to break frequency hopping is determine, first of all, your floor and ceiling, and pick a threshold that determines a channel, and then determine your channel spacing. Then determine your hopping pattern. This is actually not that simple. And our code is actually very rudimentary right now for what we have planned. The code is basically right now based on RSSI values, just watching for hops, for actual spikes in RSSI. As we get past that into predictive analysis, which I'll describe in just a minute, it will also determine a sync word for most of the channels that you've identified. So it'll guess at some channels based on the RSSI values in the first phase. It'll then sit and listen on a channel, and when information comes in, it will have specific hacked values in the registers of the RF controller that say, hand everything in and we'll analyze from here. And then we will do analysis on the packets and identify the sync word, the 2 bytes that tell the radio to start listening, is this for what we're after. So once we do that, we can set that in the radio code and not worry about it anymore. And the radio registers handle all of that nonsense. So it goes 10 10 10 10 10 10 10 10 sync word, and then we know we're sniffing. So the next phase of analysis is to predict what we think is the pattern and hop to the channels and wait for that sync word. Because the sync word is often used as a network identifier for most systems, which is why there's different sync words and it's configurable. Then we need to figure out the data rate and a couple other minuscule things. Most of these are finite. In fact, most of them have relatively few options, but because there are so many things, most people just get to about halfway through and they think, oh, this is just, okay, it's secure. I don't want to think about it anymore. Go ahead. So the goals of our code is to dispel the myth of security through FHSS. I'm sure many have already learned. Many have not. I have talked to more people over the last few years that say just what Cutaway said, or what he quoted, sorry. Our FHSS system is so fast, no hackers can ever hack it. It's like, first of all, you just told me that you really don't understand hacking, and secondly, you're wrong. Beyond where we're at, we want to take what we've already got, which is a very firm foundation for attacking FHSS in sub-gigahertz range, the ISM band 915 or 868, and we want to weaponize it. So we've got the basic building blocks. We want to add a phase or two, and we want to automate, but the automation can't come until the code base has matured more and we can trust it more. Because if you have 7 phases and phase 3 is ridiculously unreliable, well, all the rest of them will just be crap. The next stage beyond that is network sniffing, which is really basically simple. Once we have the pattern, we just tell it to go hop, sync up, and spew out the data. This platform is already ready for that. It just needs a little bit of code written to enable it. Network participation, that's a little bit more refined. We may come up with a different firmware for that because it's a different focus. It's not about breaking into the network, it's about, well, utilizing it. And the primary goal is to reduce the time to test real security. Numerous times over the past few years, FHSS systems have been not a security measure, but something that costs consultants more time before they actually get to look at the real security. I want that to stop. Go ahead. Where we're at. For our code.
Why?
What? Huh?
Why?
Why? Yeah.
That's a look of discontent, so.
So we have provided a low-cost, USB-controlled platform to play with frequency hopping systems or just sub-gigahertz systems in general. You're welcome. I hope you'll thank me once you look at it. We have calibration down. It is fast. We have most of channel identification finished and working. We've got a couple of bugs to work out there. The hopping identification is closer to being done, but still, I'd like to, before I put my stamp of approval on it, I want to do a bit more regression testing. We've got GNU plotting for those of you who like the Hackers the Movie style version of hacking, which is an amazing movie because it's just so enjoyable, regardless of any truth to it. We still need to analyze and coalesce the final data better. So, for example, we are scanning, but sometimes we're hitting the same channel 2 different scans in a row. Well, that's to be expected if your channel hopping is slow enough that our scanner is hitting it multiple times. So coalescing and dealing with it being to collapse those into that's one hit of this duration. And I personally, I promised you in the abstract that we would be using pink toys. We use pink toys a lot, but our tool is not pink yet. I definitely want to, now that I understand the USB side of things better, I would really like to port what we've done onto the IME dongle, because if you can hack a system, that's great. But if you can do it in style or using a little girl's toy, that's awesome.
I don't know, did they make pink solder mask?
Yeah.
Did you really know that? Like, yep, I have 3 boards on me.
Yeah, no doubt.
Right.
Go ahead. So we'd like to acknowledge Travis Goodspeed down here, who is good friend and the developer of many things, belt buckle and otherwise. But the most important in my life is the GoodFet, an attack-focused debugger tool that allows us to program all of our tools
And if you come
for
talk-
cheap and does good practice for surface mount soldering.
If you come talk to us at QA, Travis has been generous enough to provide us some of the boards he paid for himself. So come on up.
To give away
Yes,
to
yes.
you folks.
He's very neighborly. Mike Osman, thank you. Mike Osman is our hero. I want a T-shirt. And, well, Bill Gates, because our security industry, well, it just wouldn't be quite as awesome and fun. And Brett and Jermaine. And their baguettes. Here's a Google Code page to download our code. I don't think it's up there yet, but it will be before the end of the weekend. And how to get a hold of us. And Cutaway with a lightsaber.
Yes.
Do
All right,
we-
thank you very much, everybody.
Yeah, we are just at the edge.
So I do think we have a minute or two? No? Yes.
Semicolon.
Have you ever read Travis's Python code?
It works. It works.
I learned it from you.
Thank you very much, everybody. Oh.